So welcome back, everybody. And before we begin with the different technicalities, I wanted to say a little bit about the plans for this week and also a little bit about the plans for next week. So hopefully now you know where to find the material. And what I wanted to do first was repeat some of the things we went through last week. And then the topic for this week is another technicality which we are going to need. And these are technicalities about how we make measurements, which is going to be relevant because when we are going to calculate in the first project the eigenvalues of a system, we're actually going to set up a circuit, and at a certain point we are going to make a measurement. So we will project out the result we want, and how we make measurements is a very important aspect. This leads immediately to density matrices, and we are going to reuse the spectral decomposition which we went through last week. But I wanted to go back with some of the technicalities so that we have everybody on board. And you can see that we are going to repeat a little bit about state vectors, the tensor products, projection operators, and remind you quickly about the spectral decomposition. So the plan today is to roughly, after this introduction, is to look at the block sphere, which is another way by which we are going to illustrate the representation of one single qubit. And then with that, we are going to link with a standard representation of a qubit, of a bit, which is just given by two values, 0 and 1. Whereas when we use at the block sphere, we have a continuous set of values which the qubit states can have. And the reason why we introduce this block sphere is also that this is going to help in understanding the type of operations which we are going to do on qubits, and in particular the type of rotations which are given by these Pauli matrices. So it's a very nice way of getting a geometrical understanding of the way we represent the qubits compared to a classical bit. Now, when it comes to reading, I have a set of textbooks which I often use. So the book by Scherer is a more mathematically inspired textbook. So for those of you who want to dig more into the mathematics of some of the basic quantum mechanics, this is a pretty useful book. It also has lots of exercises with solutions, and you can download it for free. The topics which I'm covering are a little bit scattered, a little bit here and there, in both chapter 2 and chapter 3. If you wish to read about many of these things from a more computational point of view, which is going to be very relevant for the project, then Hunt's textbook is a very good guide, and you can actually download that one for free as well. So that textbook, we are essentially going to discuss some of the material in chapters 2.1 to 2.5. And then there are several other textbooks. If you go to the GitHub address, which you can look at, and there is one which has a more deeper discussion about entanglement. Now, if you go to the GitHub address, you will find, if you click on the doc link here, you will find different textbooks which I've downloaded. You can take a look at them. Some of them are more mathematical. Some of them are more hands-on. The project, if you wish to start peeping into it, there is a link here where you find the project. You can find both the PDF variant and a LaTeX file, or you can just look at the Jupyter Notebook. Now, the exercises we had last week, I've actually put two of them back here this week because they deal with the setup of these Bell states and actually setup of specific elements which we will discuss from a computational point of view next week. So next week, we are going to look at gates and how we can encode them and how we can actually make a measurement on the Bell states and see what we get. And we can also run this on Qiskit, with Qiskit, which is a software provided by IBM, which also gives us access to the IBM quantum computers. And we have up to 127 qubit machines which are freely available. We are going to discuss that next week. So next week will be a little bit more technical one where we try to implement some of the topics we've gone through the first 2 weeks. So this course has a mix of computations and basic theory. Okay. So you, I guess it's not needed to remind you of that, but the semester page is this one. I also changed the Zoom link because I've stopped being at Michigan State. So I'm now just using my UIO address. And that's going to be the permanent Zoom link for the rest of the semester. And that was also included in the email which I sent you all. Okay, so let me quickly very quickly repeat some of the things which we discussed last week. So I will go quickly through this one. And the thing which I wanted to remind you of first is a very important quantity, which is the outer product, which we are going to use again and again. And you will see that when we define so-called projection operators, which are needed when we are going to perform measurements. So we're actually going to project out a specific component of a state. And in that case, what we define is an operator which is defined in terms of an outer product of two vectors. So this is just the mathematics, which probably many of you have seen before. And these are also, I'm actually not going to go through all these because we went through them last time, but I wanted to quickly remind you about the representation which we are going to use. So we are going to use the standard bracket notation. So instead of writing a vector like X, bold-faced, you will also see that on my whiteboard notes, since it's more difficult to make a bold-faced quantity, you will see a vector with a vector sign above it, and the operators will have a hat, whereas in the text I will mainly use bold-faced quantities. I hope you can forgive me for that. And then we have inner products, which you're familiar with, and we also defined outer products. So these are things you can revisit if you want to. So this is just the outer product of a typical object which we will encounter. And they obviously live in a complex space. So a set of matrices, which we also meet again and again, are the Pauli matrices, because they are going to define specific gates. So these are two of these matrices, and these have specific commutation relations, which was one of the exercises. We are going to define the basic qubit states in terms of these vectors. So bit 0 is then going to be represented by this 2 times 1 vector, and bit 1 by this other 2 times 1 vector. So this is going to define a computational basis for 1 qubit. And these vectors can then be used. So sometimes I will write it like phi 0 like this, but in general, I will just stay with 0 and 1, as you see here. And it's easy to see that this applies. And this is the completeness relation for this basis. And this is an orthogonal and normalized basis. And you see now that if you take the trace of this object here, that is just equal to 2, as it should be. And that simply refers to all the degrees of freedom which we have here. These operators project out a specific component. So when I'm acting on the vector with qubit 1 or bit 1, then this will give 0. Whereas this gives 1, or just a vector again, the vector itself. And Q, when that acts on the vector with bit 1, that gives obviously back the vector with bit 1. And these operators are also very important because they are so-called idempotent operators, and they commute with each other, which is also easy to see. So the reason why I bring this back again is that we are going to reuse these type of quantities again and again. Then clearly the important quantum mechanical principle of superposition is there, which means that alpha and beta are so-called complex coefficients, which then define the likelihood of being in state 0 or state 1. So when I say state 0 and state 1, with a 1 qubit system, I'm actually intending this state or that state. So that's just going to, it's like when I typically say Hermitian conjugate, sometimes I just say the conjugate, sometimes I just call it the adjoint, but from the context, it should be pretty clear that this is a Hermitian conjugate, for instance. Then we have inner products, and we are always expecting that this basis is normalized. So alpha squared plus beta squared is equal to 1. And then if we act with these projection operators, what we get then, when this acts on this state, which is in a superposition of bit 0 and bit 1, then what we simply get is bit 0 times this coefficient alpha. And this is something I want to bring up because we're going to use that when we discuss measurements. Another quantity which we will play a lot with is the density matrix, because the density matrix is used as a measure of whether we have a so-called pure state, a mixed state, and also it is a quantity which allows us to calculate, let's say, the specific entropy of a system and the entropy of a subsystem. So coming back to these Bell states, which we discussed last week, which we're also going to bring up today, in the Bell state, you have a defined state for two systems, 2 bits. So you can call this system A and system B. And your beginning state is what we call a pure state because it is exactly defined by a linear combination of specific bit arrangements. When we calculate the density matrix of one of the subsystems, then we will get the strange result that the subsystem is not exactly specified, whereas the full system is exactly specified. The full system is in a specific state, but we cannot say in which state the subsystems are, which make up the full system. And this is one of these very interesting features of entanglement, which we are going to use also as a measure when we calculate the von Neumann entropy, which is normally used as a way to analyze a specific system and see whether it's entangled or not. And as you will see later, entanglement is just an essential feature for performing all the operations which we're going to do. Without entanglement, all the manipulations which we will do in order to get the eigenvalues of a specific system are going to be impossible. So entanglement plays a central role. So, and last week we also defined some specific matrices. So if this matrix acts on this specific state, which is bit 0, then it produces a state which is a superposition of bits 0 and 1. And this is called a Hadamard gate. And we are going to use that one when we initialize a circuit, because we're going to make states which then are going to be superpositions of the different computational basis states. So just to digress, yeah. No, this just gives rise to a phase when you're calculating expectation values. And you have two possibilities for the linear representation. So these are two equal ways of making a linear superposition. And yeah, so these states are also actually going to represent specific physical operations which we're going to make. And you will see in all the quantum circuits which we're going to set up, we are going often to initialize the system in a specific way. So the system could be initialized with all the objects in bit 0. But then we are making a superposition. So on every bit then, or every state we have, we are going then to create a superposition. That is a 1 qubit operation. So this is an operation on just 1 qubit. Then we are going to introduce later, and this is next week, 2 qubit gates, because we need to entangle the system. So this 1 qubit gate does not create an entangled state. It creates a superposition. I'm going to skip some of these. Then the next part is the so-called tensor products, which we discussed last week. And in that specific case, what we need to pay attention to is that a specific state, when we make up a new state in terms of this representation and this one. So this would be a state X, which is a linear superposition of bits 0 and 1, the same with Y. When we then set up a new state, which you could think of this as a one-particle state, and this is a one-particle state, this becomes a two-particle state. And the typical notation which we end up using is a compact notation like this, X times Y, instead of just carrying with us the tensor product. But what it means mathematically is that these 2 times 1 vectors are transformed into a 4 times 1 vector. So it's a vector of length 4. And then we have examples of tensor products, which you saw last time. And these are states which you can then make up. These are all orthogonal and normalized states. So you can use these 4 states here to make a new orthogonal and normalized basis, and then expand other states into that one. And as we said, you can make 3 qubits and more. So this is just a quick reminder here. So now I'm going to go back to the slides for this week. So that was a reminder about the mathematics which we need in order to represent the different states. So we are going to look a little bit closer today at measurements. So that means that when we have a superposition like this one, when we make a measurement, the system is going to collapse into one physical state. So you will never observe a superposition, but we can use the superposition as an intermediate state for computations. And that's one of the black magics of quantum computations, that you actually use the fact that you can access many more states in an intermediate step. So a measurement obviously collapses only to one of the states. So that would be either 0 or 1. And it would have probability like alpha squared or beta squared. And these are normalized. So this is some basic properties. And we've already seen these operators P and Q. And what we need now is actually to look at some other operations which we have to think of. So one very important property when we do quantum mechanics is the fact that we are dealing with unitary operators. So these unitary transformations, typically, they are self-adjoint, meaning that the matrix of a Hermitian matrix are given by what you see here. And it's unitary, where the I is a unit matrix. And the operator is self-adjoint, they commute, like we discussed last week. And that defines normally what we call a normal operator. And a very important aspect, which we are going to use again and again when we set up a quantum circuit. So when you see a circuit, what that means mathematically is the operation which you see here with a given unitary transformation, which acts on your initial state, and it gives the system in a new state. So when we acted with that Hadamard matrix on a state, that can be seen as an example of such a unitary transformation. Essentially, what we do when we solve, let's say, Schrödinger's equation for one or many particles is to find a magic unitary transformation, which gives us the exact state. So the essence of quantum mechanics mathematically is actually condensed into this equation here. So if you're solving a many-body problem, obviously, if somebody gives you the right unitary transformation, then you should be able to find the eigenvalues and the eigenvectors. But normally that one is something which, besides some simple problems, is something which you, at the end, have to solve numerically. Now, what you're going to see is that we will typically, when we solve the equations for the eigenvalues and eigenvectors in this project one, the first project, is that we actually are going to set up these operations in terms of specific rotation matrices and other matrices. And that will, at the end, give us a state which we can, through a variational approach, find the optimal representation. So we also know that the orthogonality is preserved when we have orthogonal or unitary transformations. And then we know that the Pauli matrices, this is actually one of the exercises which we have at the end today, is to show that, is to find the eigenvalues of and eigenvectors of the given Pauli matrices. The sigma Z matrix has this computational basis as eigenbasis. The sigma X matrix has a linear combination of 0 and 1 as eigenbasis. So one of the reasons why you're going often to see the sigma Z matrix popping up again and again, and why we often want to transform expressions in terms of this sigma Z matrix, is because the sigma Z matrix has bit 0 and bit 1 as an eigenbasis. And that is going to be a feature which we are going to exploit many, many times. Then let me just remind you, after this long detour, of one of the quantities which we did last week. So I'm just putting it up here, but that's the spectral decomposition of an operator. So this P of I, which you see here, that is an operator, which is given by this tensor outer product. And I can rewrite in that basis any operator in terms of its eigenvalues in that basis. So that's a very powerful statement, which we are now going to use when we look at measurements and density matrices. So in the examples here, you will find then that we have so there's some explicit examples. So if you take this state psi of A, which is a linear combination of 0 and 1, and psi of B, which is a linear combination of these two, we can then construct this matrix, which is an outer product now, which is a projection operator, which is given like this. And then if I do the same thing with B, this state B here, I have another projection operator. Then I can act with P of A on these specific states. So I can do, if I now look at the operator A, I can actually rewrite it in terms of lambda A, the eigenvalues, and lambda B here. So that would be the spectral decomposition of that specific operator A, which now has these two eigenvectors, which in turn are defined in terms of another orthogonal eigenbasis. So just keep in mind, I'm bringing this up again and again. I hope you don't get offended if I keep repeat. That's a kind of professional damage when you've been teaching for close to 40 years. Well, my daughter is always angry with me because she says that, Dad, you need to repeat it. I understood it once. You don't need to say it twice. When you've been teaching, repetition is always, I think it's beneficial. But the thing now is that the basis 0 and 1 is what we will call the computational basis. Now, physical reality doesn't need to be represented by that basis. But that basis is often chosen, so it's an eigenbasis of perhaps a simpler part of a given Hamiltonian. So often you would split your problem in something which can be solved analytically, plus something which represents the interaction between the particles, which doesn't have an analytical solution. But you know, when you have a basis, which is an orthogonal basis, then you can expand the state of the interacting system, the full Hamiltonian, in terms of that basis. So that is the standard linear superposition, which we are doing again and again when you have an orthonormal basis. So what I'm simply saying now is that psi A and psi B are eigenstates of that operator A, rewritten in terms of the computational basis. Does that sound reasonable? So then what we get when we have these two matrices, we get then a representation, or the spectral representation of that operator A, which then will be written like this. Okay? So it means I can take a given computational basis and then rephrase the solution of another problem in terms of that basis. Now, one thing I wanted to mention, and I'm going to use the slides for just some few more moments, and then I'm going to switch over to the whiteboard. And that is about the block sphere. So the block sphere is a very nice way of representing the qubits. And we are going to meet this again and again, but now I just wanted you to introduce it to you. So this is meet the block sphere, which is a very useful way of representing the qubits. So if you think of a classical system and you were to plot them, you could then just think of 2 points, 0 and 1. So that's a classical system. That is well defined. Quantum mechanically, on the other hand, since these alphas and betas are complex constants, I can rewrite this in terms of points on a sphere. And that means that I can actually, and this is going to be an exercise a little bit later, we can now actually rewrite that in terms of these as complex coefficients represented by the angles theta, the azimuthal, and the answer of the angle, where they go from theta up to pi and phi as the theta. And I'm introducing to you Qiskit, which has a visualization of the block sphere. And if I do that, I will get something which looks like this. So in this specific case, you can see now that I've chosen a specific direction in Cartesian coordinates. Now, bit 0, this one, if beta is equal to 0, bit 0, when you now use the Pauli matrices and think of this as a computational basis, bit 0 is going to correspond to the what we call the North Pole. So if I rewrite this one now in terms of 0 and 1 and rewrite it, so bit 0, like this one, is in this specific representation given by the North Pole. And stated differently in terms of the eigenvectors of the Pauli matrices, you can then see, if we now switch quickly back to the, so let's just switch to the whiteboard. So one thing which I mentioned is that if we take the Pauli Z matrix, which is given by 1, 0, 0, minus 1, this vector, with this matrix, which you can think of as an operator, has as an eigenbasis, if I act on this with 1, 0, what you get then is just plus 1 times 1, 0. So what we say then is that this is actually an eigenbasis for sigma c, which we will also label simply as C. This means that if you think of this as a projection on the z-axis, you can think of bit 0 as being the North Pole on a block sphere. So we could then say that the state 1, 0, which we have labeled as 0 here, is then given as the North Pole on block sphere. So that's a very nice way of visualizing it. The other state which we have, if I act with this one on the state 0, 1, then you will see that this gives minus 1 times 0, 1. And then it's natural to say that since this is pointing down, you can think of this as the South Pole. So these two states have a specific representation. Now, if you take the Pauli X matrix, which we'll also write like this, which is then given by 0, 1, 1, 0. If we act on this one now as an operator, so I should put hats because these are operators. If I act on this one, what we see then is that this is the same as 0, 1, 1, 0, acting on 1, 0. And that is an operator which now flips the states. So what we see then is that we started with 0. So 0 goes over to 1. Now, this operator, however, does not have 0 and 1 as an eigenbasis, as you can see, right? However, as you will see in one of the exercises this week, it has a linear combination of 0 and 1 as an eigenbasis. So if you then want to plot this on the block sphere, then you have to make up the linear combination of 0 and 1. So this is one of the exercises which you will play around a little bit with. So what you would see then quickly is a 0 and 1 are not eigenbases. Eigenstates of X. And you will also see that this is the case also for the Pauli Y matrix. So I leave that as a small exercise for you to show, because then when you have these linear representations, you can go back to the block sphere and visualize these other eigenvectors on the block sphere. So the general mathematical representation of that is something which we are going to write as. So if we now look at the mathematical expression here, this is the mathematical expression which is pretty general, which you then can use to define a qubit state, a 1 qubit state on the block sphere. And as you can see here in one of the exercises, I ask you to find the block sphere angles theta and phi for the eigenstates of each Pauli matrix. So for the Pauli Z matrix, it's pretty simple. You have the North Pole and the South Pole. Whereas so that means that the angles have to be, the angle theta have to be up, and similarly with the angle phi, which has to be 0 then. And for qubit 1, then you're pointing down. So that means that you have to rotate down to the South Pole. And then for the other ones, it will just be linear combination of these states. So one thing I'm not doing, which you will also find in many textbooks, is why you can represent this state which you have here, where alpha and beta are complex objects, and which then can be written in terms of a complex phase. And since these are complex objects, and you can write them in terms of a complex phase, you can always rewrite them in terms of cosines and sines. But I'm not going to spell out that mathematics. If you want to read more about that, there is actually in one of the textbooks which I link to. So I'm just looking at that as a kind of technical detail, but in this textbook in chapter 2, you will find a broad discussion of the block sphere. So in some cases, in this course, I will just state the results. And in other cases, I will spend more time on deriving specific theorems and results. But this is a case where I assume that this is something which you can easily figure out why it's the case. So what we're going to do now is to look at measurements. And I'm going to jump back to the whiteboard because I wanted to say a little bit about measurements. And one of the things which we are going to use now is actually the spectral decomposition of an operator. Okay, so let's switch back to the whiteboard. Because this is one of the important topics which we are going to deal with again and again here. So measurements. And now we are going to assume that we have, suppose we have a system A. This is an operator which acts on a specific state, and that has an eigenvalue lambda times some psi of A. So what quantum mechanics postulates is that mutually exclusive measurement outcomes, they would correspond to orthogonal projection operators. So just let me repeat that. So quantum mechanics, one of the postulates is that mutually exclusive measurement outcomes, that corresponds to orthogonal projection operators. So what we could say now is that these projection operators, which are projecting out a specific component, so they are mutually exclusive ones. We could now say that we are just looking at a set of operators, P0, P1, etc., up to some P of m minus 1. And in total, we have n operators, but m can be equal to or less than n. And we have a completeness relation, which states that if we sum up over I equals 0 up to n minus 1, this is given by pi. So the typical example, which we have seen again and again, is the basis 0 and 1. And if I do that, my matrix, so this 1 is simply given by a sum from I equals 0 up to 1. And then I have my I of I. And this is equal to 1, 0, 0 plus 0, 0, 0, 1, which is then equal to 1, 1, 0, 0. So that's a pretty simple example of a set of operators which we are going to use again and again. Now, in the examples here, when we discuss measurements, we are going to look at a system with just one qubit. And in order just to make life simple, and we are going to use this also to introduce the density matrices, and we will also be using the spectral decomposition. But let's now see what the probability of a given eigenvalue is defined as. So if we now have a specific eigenstate, I, and the probability of a specific I with a specific eigenvalue, we could write this as a probability of lambda I, and that is going to be given by this projection operator acting on that state, psi of A, where P of I is just one of these possible operators. So what this actually means is that we can write this as psi of A, and this is multiplied with P of I, emission conjugate acting on psi of I. Now, one thing which is important for us is that these are emission operators, so P of I is equal to P of I, and P of I squared is equal to P of I. And you can see that if you go back to these simple examples. So if you look back at the examples which we had earlier, these two cases which you see here, you see now if I square this one, it gets back to itself. And if I square this one, it gets back to itself. So these are typical examples of situations which we will encounter when we are setting up an outer product. And these outer products function as projection operators. So if I use this, then we know that this one has to be equal to psi of A of P of I of psi of A. Now the total probability for all measurements is naught, since this is a orthogonal basis we are using. So the total probability for all measurements is the sum over all the possible measurements which we have, or operators, and we will simply write this as a probability for a specific state lambda I, and this has to sum to 1. That's an important aspect because we assume that these probabilities are normalized. So another thing which I will state here, but we are coming back to the derivation of it. So when we have performed a measurement, we will be left with a new state of the system. So after a measurement, what we will call the post-measurement normalized pure quantum state. So I'm going to call this the post-measurement normalized state. And we normally think of this as a pure state after the outcome after, let me just correct that one. The outcome of a measurement, which we are going to call lambda I. This new state is now going to be given, so we have the measurement which we are performing on the original state, psi of alpha. And this is then divided by the norm, which is now psi of A of pi of I. So these are operators times psi of A. So I'm just defining these quantities. And these quantities are something now which I will illustrate with an example. So we have two examples which we're going to look at. And the first example is one where I define P0, which is just 0 and 0, and P1, which is equal to 1 and 1. And you see quickly then that if I rewrite this as a P of I over these two possibilities, this sums to the identity matrix. So remember now that P of I squared is P of I. And if I sum up P of I, if you go back to that simple example we have here, this gives us simply the identity matrix. Okay. So the next thing I'm going to do now is to assume that we are in this state. So in the beginning, we are in a superposition of the two computational basis states, 0 and 1. And now I perform a measurement. So I'm now going to say, what is the probability of this psi for element 0? So that will be the same as us setting up this expectation value, psi of P0, P0. So sometimes it happens that I forget to put the hat. You have to forgive me for that. That is simply me just forgetting. If I do that, then what you see is that this becomes equal to alpha complex conjugate 0 plus beta complex conjugate 1. And this is multiplied now with the operators. So I would have, since I'm doing 0, it's 0, 0. So what we have then is that this one is the same as what you have here. And this is then multiplied with alpha times 0 plus beta times 1. And 0 projects out just 0, because if this one now acts on 1, that is 0, because it's an orthonormal basis. And what we are left with then is simply alpha squared, as it should be. So the result of such a measurement is actually given by that specific state. Then, if I look at my normalized state after the measurement, so you know that this measurement here projects out state 0. But now it projects out state 0 with an alpha in front of it. So it's not normalized. So my normalized post-measurement state is going to be this psi 0 prime, and that has obviously to be given by this operator on psi, and then I have to normalize it because my state as it comes out is not normalized. So I've called this psi 0 prime as the normalized post-measurement state. And when I normalize it then, I obviously get alpha divided by alpha multiplied with 0. So then you see where this normalization constant, why that comes in, because when I make the projection, I get a coefficient alpha. So my new state, the post-measurement state, is not normalized. And you can see then, if I do the psi 1, it shouldn't come as a surprise that we get beta divided by the absolute value of beta times 1. And what we say then is that the projection makes psi collapse to either 0 or 1. So this becomes important. Now just keep this in mind for a little bit later, because when we are setting up the circuits, we are going to make measurements on the different bits we have, and the final result will then give us a given projected state with an amplitude in front of it. And we are going to repeat this again and again to get a statistical valuable result. So we normally call one such measurement as a shot. And then you just repeat it again. So shot is just some kind of, I would say, parlance which has been used in the community. But you see, this sounds pretty obvious, right? So this is the way we think in terms of measurements. So after the break, we're going to rewrite this in terms of the density matrix, which is going to give us a very compact way of looking at different quantities. Any questions before we take a break? Okay, so I'm just gonna stop this one. Okay, so let's take a look at this kind of measurement stuff, and let's take a look at the further example along much of the same lines, and we are going to use that one to rewrite everything we have here in terms of something which we are going to call the density matrix. So let's now look at the new example. Again, we are going to have a qubit state, which is equal the previous one, with the same linear combination with two complex coefficients, alpha and beta. And what we found then is that the probability, just to quickly remind you of that, the probability of observing this specific outcome is something which we defined as psi, and then we had this projection operator of psi, and that was equal, in this specific case, to alpha squared. Now, there is an important quantity which we are going to see again and again and again, and it's going to pop up in connection with experiments. That means measurements, and it's also going to pop up when we are going to study the degree of entanglement, and whether we have a pure state or what we are going to call a mixed state. And this is our first encounter, so that is the density matrix or the density operator. It becomes a matrix because we are going to use a finite basis, but you will often see it also called operator. So we are going to use this interchangeably. And in this case, we are now going to define this density matrix, rho, in terms of the basis which we just defined, this basis psi. Now, there's one thing which I'm going to state now and then say a little bit more about later. And that's what we mean by a pure state. So a pure state is a state which is exactly defined. We know that the system is in that state. So if you think of the helium atom in its ground state, and we know that it is in the ground state, we would say that that wave function, which represents the ground state of the helium atom, can then be used to define the density matrix. And that would be a pure state because we know exactly how to define it. So if I take that specific example, which we have here, that means this state here, and then calculate the density matrix, what we see now is that this quantity is going to be equal to alpha squared. And then I have alpha times beta complex conjugate. I have complex alpha times beta, and then beta squared, like that. Now, one thing which I know then, and which we saw from previous calculation, is that P emission conjugate times P0 is actually equal to 100. And this is an idempotent operator, as we discussed. So if I multiply this matrix 100 with my density matrix, or density operator, I have an alpha squared, alpha times beta, complex alpha, beta squared. If I do that, this is nothing but this P0 acting on this rho psi, and I'm putting hat on these to indicate that these are matrices operators. And if I do that, what we get, if I perform the calculations, I get alpha squared, alpha times beta, and then I have 0. If I look at this quantity and go back to what we found when we performed the measurement, we got this when we collapsed the wave function with the P0 operator. What we do then, if we now look at this one, we can then see that this probability of psi 0, or after the measurement, is the same as the trace of P0 times rho psi. And this quantity here is exactly, if you look at this object here, that is what we have here. So if I trace out, perform the trace, this is actually equal to alpha squared. So I can now rephrase the measurement in terms of a specific projection operator. And I used here the properties that P squared is equal to P, and P0 squared is equal to P0. And that means that I can rewrite my probability of the measurement which I'm making, the probability of that one, the outcome, to the trace of the projection operator multiplied with the density matrix. So in general then, if I'm looking at a general probability, the probability of a specific outcome, let's just call this X. In our previous case, this was just the state 0. But now you could just think of a general specific state X, which is defined by a specific projection operator. That will be given by P of X, where this simply is just X times X, P of X, and then it's multiplied by the specific density matrix of that system which we have at hand. So now I'm just picking a random state which defines rho, the density matrix, and then I'm performing a measurement on that specific state. So this is just another way of rewriting the expectation value of a specific quantity or the measurement which we are discussing in terms of a density matrix and the projection operators. Sometimes in many textbooks, you will see this being replaced by an operator M or MX for measurement. I prefer to keep P because these are actually projection operators. But you will often see the M, the operator being labeled as M. Now, there is another thing which we can do now with the density matrix, which is now coming handy. So if we now look at the density matrix and a specific state psi, in general, that specific state psi is a sum over all the possible linear combination of an orthogonal and normalized basis. So in principle, this has a coefficient multiplied with a basis. This is the standard superposition which we get from a linear operator. Okay? If you then look at the density matrix, that means that rho for this specific state psi can then be written as, so just one thing, I'm just leaving the initial values of the sum and the final values unspecified, because in practical calculation, we will always have a finite basis, but in general, the basis I is infinite. So I'm just leaving this I, which you see here, unspecified. But in actual calculations, we will always have a finite basis. So if we do that, you will see that this is the same as C of I multiplied with I of I. Now, that coefficient is nothing but the likelihood of being in specific state I. So this one, and now I have to be careful because I will replace the C of I with the probability of being in a specific state I. So this should be a little p, not an uppercase P. So hopefully you can see that these are uppercase letters, whereas the little p is meant to be a probability. And I will try to be consistent and not have hats on that, whereas operators have hats. So this is a probability of being in a state I. So that means that I can rewrite my density matrix as, and this is the spectral decomposition of the density matrix. So this is the spectral decomposition. And now we get use of what we discussed last week in terms of the spectral decomposition of an operator. So that's the density matrix as a spectral decomposition. So what we can do then when we have this is now to look at some specific examples. And the cases we're going to look at now are the famous Bell states. So let's take the Bell states, because we will also look at how we can encode them next week. And we are going to use the Bell states as our first example where we calculate expectation value or perform measurements. And you will see that the results of a measurement of these Bell states is going to be 50% for one option and 50% for the other one. And this is what we should get when we perform a measurement. So let's look at the Bell states, because this is a classic case. Oh, Bell states. These are so-called entangled states because they cannot be written as product states. Another way of stating that in terms of probabilities, how many of you have taken a course in statistics and probability? And not everybody. Okay, so you know that if you have independent events, then the probability is just the total probability, is a product of the independent events. If you don't have independent and identical variables, then the probability is a complex function of all the variables. So if you have product states, this is the same as you having variables which are independent of each other. If you have an entangled state, that is the same as you having a probability for the system, which is a complex function of all the possible variables. And you cannot disentangle the different variables. Yeah? Yes, exactly. Good point. Okay, so let's look at the Bell states and go through some of the basic mathematics here. So this is just going to be a little bit boring exercise for the rest of the year, for the lecture here. But I just wanted to go through that. So these states, and that was one of the exercises last week, are states which we now can define as a entangled basis, which we cannot rewrite as a product states. So just remember that this 0, 0 is actually the tensor product of system A. So you can think of a system A or a particle A, where we then take the tensor product with B. And that is the same as 1, 0 tensor product with 1, 0. And that is the same as 1, 0, 0, 0. So we will always use this notation. So you could think of this as a two-particle system, or it could be two complex systems, A and B, which have two low-lying states, which we identify with qubit 0 and qubit 1. And this is the same as 1 of A, 1 of B, and that becomes simply 0, 0, 0, 1. So that's one of the states. And you see that if you normalize it, you will see that this is already normalized. The other three states are the following. So I have a phi minus, which is just the same state as before, but with a minus sign. I have a psi plus 1 over square root of 2 of 1, 0 plus 0, 1. And finally, I have a psi minus, which is simply this state here, but now with a 1, 0 minus 0, 1. So let's just look at one of these states. So what I could do now is to define the density matrix for this phi 0. So this state here is what we will call a pure state. The reason for that, if you're now thinking of this as a two-particle system or two-state system, is that this state is exactly defined for us. So we know what it looks like. So we know that qubit in A is in state 0, and here it's also state 0 in state system B, and then we also know what it is here. So we would say then that the state is well known, and then we normally call it a pure state. So what I'm going to do now is the exciting exercise of actually calculating this quantity. And I'm going to give you the answers. So this is going to be 1/2, obviously. And then I'm going to have 0, 0 plus 1, 1 multiplied with 0, 0 plus 1, 1. So what I'm going to do now is simply to calculate these outer products. And I hope you don't get offended if I just, yes, one of these outer products is just going to be this one, 1, 0, 0, 0, with 1, 0, 0, 0. And that is the same. I'm just going to do one of them because this is not very exciting. Okay. So what I need to do now is simply to take all these outer products. And if I do all the outer products correctly, what I'm going to get is that this density matrix of this phi plus, which is now equal to phi plus, this is going to be equal to 1/2. Then I have 1, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 1. So that's my density matrix. Now, when I have the density matrix, I can now perform measurements. But you should note another thing here. If you look at this one, so now let's just call this for raw, and let me put hats. So I skip the subscript with phi plus. So pay attention to one thing, and this is actually very interesting. So rho squared for a pure state is given to rho. That means that the trace of rho squared is equal to the trace of rho, and you will see that that is equal to 1. And you see that if I take the trace here, I have 1 plus 1, 2, divided by 2 is 1. If I square it, this matrix is exactly the same, but then I have 1 divided by 4. But no, if I square it, I will get 2 here, 2 here, 2 here, and 2 here. So if I square it, then there will also be a 1/4. So I will have 2 plus 2, 4, divided by 4 is 1. And what you see now is that trace is equal to 1. And that is used as a measure for whether you have a pure state or what is called a mixed state. I'm coming back to what a mixed state means. So remember now that a pure state means that you know everything about the system. A mixed state must obviously mean that you don't know everything about the system. Yeah? Yes, exactly. Yeah, exactly. So this is the same as if you were to sum over the probabilities. If you square this object, that would be the same as the sum of the probabilities, which should be 1. Now, when you now have this object, we can now make measurements. So let's make a measurement on one of the states. So if we now go back to measurements, suppose now that we want to look at the projection of qubit 0 in system A. So if I now look at this 0, 0, this is the same as A, system A, and system B. So one assumption which we'll often see in these textbooks on quantum computing is that we assume that these are distinguishable systems, which is normally not the case in real systems, because if you're dealing with fermions or bosons, these are indistinguishable particles. But let's assume that these are distinguishable systems. What I'm going to do now, I want to make a measurement where I project out system A and bit 0. So let me define now a P0, which is simply 0A. So this is the outer product, which I'm taking. But then I'm leaving B unaffected. So that means that I need to perform a tensor product with the identity matrix for system B. So system B is left unchanged. So I'm just going to make a measurement on one of the bits. This is, in this case, a 2x2 matrix. And we know that this is also a 2x2 matrix. So if I look at this one, this is going to be 1, 0, 0. So that's the qubit 0 in system A. And then I have the tensor product with the identity matrix 1, 1. That gives me a new matrix. So if I do the algebra correctly, this should be 0, 0, 0, 0, 1, 0, 0, and then I have just zeros all the way left here. So this is now my 4x4 matrix, because remember that the object which I'm having is now a vector of length 4 times 1. My density matrix is a 4x4 matrix. So when I do the algebra here, I have to make sure that the matrices have the correct dimensionalities. Okay, so when I make a measurement now, what I'm going to have is a measurement where I want to project the probability of phi plus and 0. And when I say 0, then I'm actually meaning the one of the particles which I have. So what I'm going to do now with this operator, I'm going to calculate with phi plus. So this is system A and B, and I now want to project out one of them. And now I have this operator P of phi plus, which then, when I plug in everything, gives me 1/2. And the only one which gives something which is different from 0 is actually this state. The 1 state is not going to give me anything. So I end up with 1, 0, 0, 0, 0, 1, 0, 0, multiplied with 1, 0, 0, 0. And what I see then is that I get equal to 1/2. So when we are now going to make measurements on one of the qubits next week, this is what we should get. Then you can do the same with the probability of phi plus 1. And in that case, you will also find, when you set up this matrix M1, that this is equal to 1/2. So I leave that as a small exercise to you guys. Now, there are some important properties of this this density matrix. And this is something which is going to be important when we now are going to project out the density matrix for a subsystem. So now we were looking at the density matrix for the full system. So the question is, suppose now that we have a row for system A and B. If I have this for system A and B, then you may ask, what is the density matrix for system A or system B? Now, the reason why I'm going to go through this calculation now is that we are going to need that one next week when we discuss the entropies. And this is going to provide us with a measure of the degree of entanglement and whether this is a mixed state or not. So so it serves, this is a technical aspect, but it's going to serve as an important quantity when we are going to study systems in order to understand whether we are dealing with a pure state or a mixed state. So what we need to do now is to trace out one of the systems. So this matrix, rho of A, this density matrix, is actually going to be given by us tracing out subsystem B of the full system. It means that B must be us tracing out there is a parallel to this. Some of you may have encountered in probability theory something which is called the marginal probability. So the marginal probability is you integrating away the other degrees of freedom, and you're only left with 1 degree of freedom. So let me just give a kind of parallel to this. Suppose you have a probability which depends on X and Y. But then you want only the probability with respect to X. So that means that you can then find the marginal probability P of x, for instance, which then would be given by an integral, or it could be a sum if it's a discrete probability of px or y. So you're integrating away one of the degrees of freedom, and you're only interested in one of the subsystems. So suppose now you have a system like atomic helium with 2 electrons, and you want to find, so somebody gives you the wave function. This is a pure state, the ground state of atomic helium. With that one, you can calculate the density matrix. But then you ask yourself, what can I say about one of the electrons? Can I define this as a pure state? Or is there an ambiguity? So one thing we are going to see now when you have entangled states is that when you trace out the density matrix for a subsystem, you can define the full system perfectly, but the subsystem is left undetermined. And that's one of these important aspects of entanglement, which we will use again and again. So let's look at this other technicality. So what we need to do now is to trace out one of the subsystems. So let's take a look at the Bell state again. This is one of the examples. And then I will leave it as an exercise to look at the product state, which is actually much, much easier. So if I now look at the specific Bell states, and I now want to trace out, so for the Bell state, and let's go back to this phi plus state. So in this specific case, my rho of A, B, the full system, is then given by this matrix which we had before, 1, 0, 0, 1. So I'm just repeating the matrix, 0, 0, 1. So this is a matrix which is a 4 by 4 matrix. And in this case, it contains only real numbers. So when we are doing these operations now, we have to be careful with the dimensionalities. Now, what I want is now to trace out the different qubits. So I would like to have the qubit, the density matrix rho of A, which is now given by us tracing out rho of AB. And when we trace it out, this is going to have 0 in the system B. And then I have the density matrix. And then I'm tracing out, so I'm putting a B here as a subscript, plus a 1 in system B, rho of AB, a 1 in system B. So I'm tracing out the subsystem B. I want to get rid of these degrees of freedom. So let's now look at how we can do that. So if I now look at the system A, this is actually 1, 0, and it's a tensor product with an identity matrix. So this is left unaffected when I'm tracing out. So 0, 0, 1, which then becomes a matrix of 1, 0, 0, 1, 0, 0, 0, 0, like that. Then what I'm going to do now, so this is a 4 by 2 matrix. My matrix, which I have here, is a 4 by 4. So when I'm performing the multiplications now, when I'm tracing out the system which I want to get rid of, I need to have a 2 by 4 matrix, which is given by 1, 0, 0, 0. And then I have 0, 1, 0. And this is now multiplied with my full density matrix. So this is rho of AB, 1, 0, 0, 1, 0, 0. And then I get 1, 0, 0, 1, like that. And if I write it out, this is going to be given by 1/2. So I have a 2 times 4, a 4 times 4, a 4 times 2. So this gives me a 2 by 2 matrix at the end. And when I do the algebra, what I get is 1, 0, 0, 1. And this is 1/2 1. Now, if I take trace of this row of A, which by the way, so this is row of A, which is also equal, and you can find that if you do the algebra, which is row B, so they are equal. If you now look at what we have here, if I take the trace of the square matrix, and if I have a pure state, that should be equal to the trace of the density matrix. But in this case, if I square this matrix, I get 1 divided by 4, and I get 2 on the trace, which means that what I get here is just 1/2, so that is less than 1. So if the trace is less than 1, this is normally called a mixed state. And the reason for that is that if you look at this density matrix which you get, if you write it out in terms of the components, this is going to be equal to rho B. It's going to be equal to 0, 0 plus 1, 1 divided by 2. Now, what you have now is a remarkable result. Because if you go back to the case which we had here with the Bell state, in this specific state, no, not here, but we had it, where did we put it? Exactly this one. This state here is perfectly well known. We know in what kind of state the system is. Now, when I now project out to the subsystem, my subsystem is in an undetermined state. So what you see now is that the full system is perfectly known. However, qubit A or B, in this specific case, is in a mixed state. So we would call this for a mixed state. So that is a state about which we apparently do not have a maximal knowledge of. So this is one of these remarkable aspects of entanglement. So as a summary, what you can say then is that if trace, and we are coming back to this next week as well, so I'm going to repeat this, I just wanted to bring up these technicalities, and then next week we are going to discuss it at a little bit deeper level. This is equal to 1 if we have a pure state, as you saw for the Bell state. And then the trace of rho squared is less than 1 if we have a mixed state. Keep in mind that the state we started with is an entangled state because it cannot be written as a product, a set of products of tensor operations. So the state we started with is an entangled state already, but it is also a pure state. So you can have entangled states which are not pure states, but a pure state means simply that you would then find that the trace here of the system is equal to 1. And this has important consequences because the density matrix is proportional with a probability. And you will see next week that we can define a quantity which is called the von Neumann entropy in terms of the density matrix. And the von Neumann entropy, or the entropy itself, is a useful way to classify whether we know something about a system or if we have minimal knowledge. So if the entropy is 0, that means that we have a pure state and we know everything about the system. So the entropy represents the maximization of an unlikely event. So it's a mathematical, entropy is a mathematical way to measure which states are unlikely. If it's likely, it means you know exactly that you're in one state, then you have log of 1, which is 0. There's one state. So the entropy is an extremely usable measure for classifying whether you know something about the system or not. And then you see that the mixed state, which we have here, is a system where we don't know whether this system A or B is in this state or in that state. And when we then are going to calculate the entropy of that state, we will get a value for the entropy which is different from zero. So next week, we will discuss the von Neumann entropy. And then we will have a more technical session next week where we look at how to calculate these Bell states and how to actually perform a measurement on the Bell states, writing our own code or using Qiskit. So that next week is going to be more hands-on. We do have exercise sessions after now, if you have time to be here. And Odin here is in the back. He is just eagerly waiting for you guys. So am I. So feel free to hang around if you can. There's a set of exercises. If you scroll down, this is the last thing I'm going to say today. If you scroll down, let me just bring up that one. So most of the things which you saw on the whiteboard are also in the slides here. But you will find also a set of exercises here. So there's these exercises 1 and 2 actually from last week. And we will discuss this in more detail next week as well. But then we have some simple exercises here about reduced density operators and so on. So next week, discussion of entropy entanglement, and then we're going to look into more details into gates and circuits and how to perform operations on states. And that means also a computational element. Okay, so let me stop here.